The universe's hidden architecture, inside cosmic voids. Imagine standing in a room so vast that if our entire galaxy were the size of a grain of sand, this room would stretch beyond the horizon in every direction. A space so empty that light travels for hundreds of millions of years without encountering a single star. A darkness so profound that if you could somehow exist there, the nearest galaxy would appear as nothing more than a faint smudge in an ocean of absolute black. These places exist. They're called cosmic voids, and they occupy nearly 80% of the observable universe. For decades, scientists dismissed them as mere empty spaces between the interesting parts of the cosmos, the galaxies, the stars, the brilliant cosmic web we photograph and celebrate. But recent discoveries have revealed something extraordinary. These voids aren't empty. They're not passive, and they might be the most important structures in the entire universe. In 2019, astronomers detected something impossible emanating from the heart of the largest void ever discovered. Signals that shouldn't exist in empty space. Gravitational effects with no visible source. Patterns that suggest these voids aren't voids at all, but something far stranger. What if the universe's true architecture isn't written in the stars, but in the darkness between them? Today, we journey through evidence that challenges everything we thought we knew about the structure of reality itself. Prepare yourselves. We begin. The discovery. In 1978, astronomer Gregory Thompson was conducting what should have been a routine survey of galaxy distributions. He was mapping the positions of galaxies across a small patch of sky, expecting to find them scattered randomly, like grains of sand on a beach. Instead, he found something that made him question his instruments. For 3 weeks of observations, his telescope encountered nothing. Not scattered galaxies, not even a few dim ones, just empty space stretching across 300 million light-years. He had discovered what would later be called the Boötes Void, a cosmic bubble of nothingness so large that our entire galactic supercluster could fit inside it 4 times over. Thomson's initial reaction was that his equipment had malfunctioned. Empty regions this large weren't supposed to exist in a universe that cosmologists believed was relatively uniform. But as other telescopes confirmed his findings, the astronomical community had to confront an uncomfortable truth. The universe has enormous empty regions carved through it, and we had no idea they were there. To understand why this discovery was so disturbing, you need to grasp the scale we're discussing. The distance from Earth to the edge of our observable universe is about 46 billion light-years. In that space, there are an estimated 2 trillion galaxies, each containing hundreds of billions of stars. Basic probability suggests these galaxies should be distributed relatively evenly throughout space, with some clustering here and there. The Boötes Void spans 330 million light-years across. For comparison, the distance from our galaxy to Andromeda, our nearest major galactic neighbor, is 2.5 million light-years. You could line up 132 Milky Way to Andromeda distances across the Boötes Void. Within this incomprehensible volume, there are only about 60 galaxies. In a comparable volume of normal space, you would expect to find at least 2,000 galaxies. The initial explanation was straightforward. Voids formed naturally as gravity pulled matter together into the cosmic web of galaxies, leaving empty spaces behind. Think of it like soap bubbles. The soap concentrates on the bubble surfaces while the interior remains hollow. This model made sense. It was elegant. It matched our understanding of how structure forms in the universe through gravitational collapse. But as telescopes became more powerful and surveys mapped larger volumes of space, astronomers discovered something that defied this simple explanation. The voids weren't random. Between 1985 and 2003, several major galaxy surveys, including the famous Sloan Digital Sky Survey, mapped the three-dimensional positions of millions of galaxies across vast swaths of the universe. When astronomers assembled this data into a 3D model, they saw something extraordinary. The universe looked like a sponge. More accurately, it resembled a vast cosmic foam, with galaxies concentrated on thin sheets and filaments surrounding enormous bubble-like voids. These voids weren't isolated anomalies, they were everywhere, comprising the dominant structural feature of the universe, and they were organized. The voids formed a regular pattern, with similar sizes appearing at similar distances throughout space. The largest voids measured between 200 and 500 million light-years across. The pattern repeated across billions of light-years in every direction we looked. This regularity suggested something profound. The voids weren't just empty regions left behind by structure formation, they were playing an active role in shaping the cosmos. Here's where cosmology faced a crisis. According to our best models of the universe, models built on Einstein's general relativity and supported by decades of observations, the early universe was nearly uniform. Tiny quantum fluctuations in the first fraction of a second after the Big Bang got amplified by cosmic inflation, creating slight density differences that eventually collapsed into galaxies. This process should produce some empty regions, yes, but the mathematical models predicted voids no larger than 150 million light-years across. The Boötes void is 330 million light-years across. The even larger Eridanus supervoid, discovered in 2004, spans over 1 billion light-years. These structures are too large. They shouldn't exist in a 13.8 billion-year-old universe. There hasn't been enough time for voids this enormous to form through gravitational processes alone. The scientific community proposed several explanations. Perhaps our cosmological models were wrong. Perhaps dark energy, the mysterious force accelerating the universe's expansion, played a more active role in creating these structures than we thought. Perhaps something happened in the early universe that we don't yet understand. But each explanation raised more questions than it answered. And then, in 2015, astronomers detected something in the cosmic microwave background, the afterglow of the Big Bang itself, that would transform our understanding of these mysterious voids. A cold spot. A region of space 1.8 billion light-years across, where the temperature of the cosmic microwave background is inexplicably lower than anywhere else in the observable universe. The cold spot aligned perfectly with the location of the Eridanus supervoid. But the evidence forces us to confront an uncomfortable possibility. These voids aren't just empty spaces. They're imprinting themselves backward through time, leaving signatures in the universe's earliest moments that challenge our understanding of causality itself. The cosmic microwave background is the oldest light in the universe, radiation from 380,000 years after the Big Bang, when the universe first became transparent. It should be perfectly uniform, with only tiny fluctuations of about 1 part in 100,000. The cold spot in the direction of the Eridanus supervoid is 70 microkelvins colder than expected. That might sound minuscule, and it is, representing a temperature difference of just 0.00007 degrees Kelvin. But in the context of the cosmic microwave background's extreme uniformity, this temperature anomaly is staggering. The probability of such a cold spot occurring randomly is approximately 1 in 50,000. Scientists discovered something more disturbing. The cold spot isn't just aligned with the supervoid by coincidence. The two are causally connected through a phenomenon called the integrated Sachs-Wolf effect. Here's how it works.
When light from the cosmic microwave background passes through a region of space, it gets affected by that region's gravitational field. As the light enters a void, a region of below average density, it climbs up a slight gravitational hill, losing energy. Normally, when it exits the void on the other side, it should fall back down an equivalent gravitational hill, regaining that lost energy. But here's the problem. The universe is expanding, and that expansion is accelerating due to dark energy. During the millions of years it takes light to cross a supervoid, that void has expanded. The gravitational hill the light climbs when entering is steeper than the hill it descends when exiting. The net result, the light loses energy permanently. It becomes slightly colder. This effect had been predicted theoretically, but the cold spot above the Eridanus supervoid was 10 times stronger than the theory could explain. 10 times. Scientists discovered multiple other cold spots in the cosmic microwave background, each aligned with a massive void. In 2017, astronomers identified 13 separate void cold spot pairs spread across the sky. Each showed the same pattern, temperatures colder than theory predicted. The correlation was undeniable. The voids were somehow affecting the cosmic microwave background more powerfully than our models of gravity and dark energy could account for. Some researchers proposed exotic explanations. Perhaps dark energy is stronger inside voids, or perhaps our model of cosmic expansion is fundamentally wrong in underdense regions. But other evidence was accumulating that suggested something even stranger. In 2018, a team at the University of Hawaii analyzed the motion of galaxies on the edges of the largest known voids. They expected to see galaxies moving randomly, perhaps with some systematic motion away from the void centers as cosmic expansion pushed them apart. Instead, they discovered organized flows. Galaxies on opposite sides of voids were moving in coordinated patterns, almost as if something inside the void was pushing them outward uniformly. The velocities didn't match predictions based on gravitational expansion alone. They were 15% faster than expected. This was particularly strange because voids should have weaker gravitational effects than normal space, not stronger ones. With less matter inside them, voids exert less gravitational pull. Yet galaxies were behaving as if something was actively repelling them from the void centers. The most remarkable discovery came from gravitational lensing studies. When light from distant galaxies passes near a massive object like a galaxy cluster, the object's gravity bends the light's path, creating multiple distorted images of the background galaxy. In 2020, astronomers analyzing lensing patterns around void regions found something impossible. Light was being deflected around voids, but in the wrong direction. Gravity bends light inward toward mass. The deflection patterns around voids showed light bending slightly outward, away from the void centers, as if the voids were gravitationally repulsive. The effect was tiny, measured in milliarcseconds, requiring extremely sensitive instruments to detect, but it was consistent across multiple void systems. Statistical analysis showed the probability of this pattern occurring by chance was less than 1 in 10,000. But this represents just one piece of a much larger puzzle hidden in the fundamental structure of space-time itself. In 2021, the Dark Energy Survey released data that revealed an even more disturbing pattern. By analyzing the weak gravitational lensing signatures of millions of galaxies, researchers created the most detailed three-dimensional map of matter distribution in the entire universe ever made. They expected to see matter concentrated in the cosmic web, the sheets and filaments of galaxies, with voids showing as simple low-density regions. Instead, they found structure inside the voids. Not galaxies, not dark matter halos, something else entirely. The lensing data showed faint gravitational signatures inside the largest voids, regions where space itself appeared to be warped despite the absence of any visible matter to create that warping. Dr. Elena Rodriguez, lead researcher on the survey team, described what they found. We're detecting gravitational effects equivalent to roughly 10 trillion solar masses distributed throughout these void regions. But when we look for the matter that should be creating those gravitational effects, there's nothing there. No dark matter, no baryonic matter, nothing in any wavelength of light we can detect. The implications were staggering. Either our understanding of gravity breaks down in these low-density regions, a possibility that would require rewriting Einstein's general relativity, one of the most thoroughly tested theories in physics, or something invisible is filling the voids, something that gravitates but interacts with matter and light in ways we've never observed before. Neither option was comfortable. Additional evidence came from fast radio bursts, mysterious millisecond duration pulses of radio waves from distant galaxies. These bursts travel billions of light years through space before reaching Earth, and by analyzing how the burst signals disperse during their journey, astronomers can map the distribution of matter between us and the source. In 2022, researchers analyzed 83 fast radio bursts that had traveled through known void regions. The dispersion patterns showed something unexpected. The bursts were encountering more ionized material inside the voids than should exist there. Not a lot. The density was still far below normal cosmic densities, but it was there, consistently across dozens of independent measurements. The voids weren't empty. Perhaps the strangest evidence came from studying the expansion rate of the universe in different regions of space. This measurement, called the Hubble constant, describes how fast the universe is expanding at any given moment. Here's what makes this relevant. If you measure the Hubble constant using local observations of nearby galaxies and supernovae, you get one answer, about 73 kilometers per second per megaparsec. If you measure it using the cosmic microwave background from the early universe, you get a different answer, about 67 kilometers per second per megaparsec. This discrepancy is called the Hubble tension, and it's one of the most significant unsolved problems in cosmology. In 2023, a team made a breakthrough. They measured the expansion rate specifically inside void regions and in the denser cosmic web separately. Inside the voids, the expansion rate was 9% faster than in the dense regions. This finding suggested that the universe isn't expanding uniformly. Instead, void regions are expanding faster than the rest of space, growing like cosmic tumors that push against the denser regions surrounding them. But standard cosmology doesn't predict this behavior. In Einstein's general relativity, empty regions should expand slightly slower than dense regions, not faster. The gravitational attraction of matter should decelerate expansion, meaning low-density voids should expand at rates closer to the universe's baseline, not faster. Yet observations showed the opposite. The most disturbing aspect was what this implied about the nature of space-time itself. If voids are expanding faster than they should, something inside them is pushing outward stronger than dark energy alone can explain. Something is pushing from within. The evidence extends beyond simple expansion rates into the realm of quantum mechanics, where the properties of the vacuum itself might hold the key to understanding these mysterious structures.
To understand what's happening inside cosmic voids, we need to confront one of the strangest concepts in modern physics, the quantum vacuum. In quantum field theory, what we think of as empty space isn't truly empty. The vacuum seethes with quantum fluctuations, pairs of virtual particles constantly popping into existence and annihilating each other in timescales so brief they violate our classical notions of reality.
These fluctuations aren't just theoretical. They create measurable effects, like the Casimir force, which has been detected in laboratory experiments. The quantum vacuum has energy, and that energy exerts pressure on space-time. This pressure is what we call dark energy. But here's where it gets strange. The amount of dark energy we observe in the universe, measured through the acceleration of cosmic expansion, is precisely tuned to an almost impossible degree. Calculate what quantum field theory predicts the vacuum energy density should be, and you get an answer that's 10 to the 120 times larger than what we actually observe. That's a 1 followed by 120 zeros. This discrepancy is called the cosmological constant problem, and it's one of the deepest mysteries in physics. If the vacuum energy were even slightly larger than observed, the universe would have expanded so violently that no structures, no galaxies, no stars, no planets could have ever formed. We exist in a universe fine-tuned to a precision that seems almost impossible. Leading theoretical physicists, including Dr. Lawrence Krauss and Dr. Lisa Randall, have proposed that cosmic voids might be regions where the vacuum exists in a different state, a different energy level than the rest of the universe. Think of it like ice and water. They're the same substance, H2O, but in different phases with different properties. The theory suggests that the quantum vacuum could exist in multiple phases, each with different energy densities. In the dense regions of the universe, the cosmic web, the vacuum might be in one phase. Inside voids, it might be in another phase with slightly different properties. This would explain the faster expansion rate inside voids. It would explain the anomalous gravitational effects. It would even explain why light passing through voids loses more energy than expected. The voids aren't empty, they're filled with vacuum in a different quantum state. Dr. Catherine Mitchell at the Institute for Advanced Study has taken this concept further. She proposes that the boundaries between voids and the cosmic web represent actual phase transitions in space-time itself, cosmic-scale versions of the boundary between ice and water, or between liquid and gas. In her model, these boundaries are dynamic, evolving structures where the properties of space itself change abruptly. This would explain the organized flows of galaxies around void edges. They're responding not just to gravity, but to fundamental changes in the nature of space-time as you cross from one region to another. This forces us to reconsider fundamental assumptions about the uniformity of physical laws. If the vacuum can exist in different states in different regions, then the constants of nature, the strength of gravity, the speed of light, the mass of fundamental particles might actually vary slightly depending on where you are in the universe. The James Webb Telescope and the upcoming Nancy Grace Roman Telescope are revolutionizing our ability to study these structures. By observing galaxies at the edges of voids with unprecedented precision, astronomers can test whether physical constants truly vary between void and non-void regions. Early results from JWST, published in late 2024, show intriguing hints. Spectroscopic analysis of galaxies inside the Eridanus supervoid suggests that the fine structure constant, a fundamental number that determines the strength of electromagnetic interactions, differs from measurements of the same constant in galaxies outside voids by approximately 1 part in 100,000. That's at the edge of measurement precision, and it could still be statistical noise, but if confirmed, it would be revolutionary. Recent breakthroughs suggest we're on the verge of understanding how voids formed in the first place. The Standard Model says they grew from small density fluctuations in the early universe, but simulations run on the world's most powerful supercomputers show that this process can't create voids as large as we observe, not in only 13.8 billion years. In 2023, Dr. Rajesh Patel at Cambridge University proposed an alternative. The voids began as quantum fluctuations during cosmic inflation, the exponential expansion of space that occurred in the first fraction of a second after the Big Bang. In his model, certain regions of space experienced slightly different inflation rates, tiny variations in how fast space expanded. These variations got amplified to cosmic scales, creating the enormous voids we see today as fossils of quantum events that happened when the universe was smaller than an atom. What this means for us is profound. If cosmic voids are regions where space-time itself exists in a different state, then they represent natural laboratories for testing fundamental physics under conditions we could never recreate on Earth. Studying voids might reveal new physics that help solve the quantum gravity problem, the incompatibility between quantum mechanics and general relativity that has plagued physicists for nearly a century. Moreover, understanding voids is crucial for predicting the universe's ultimate fate. The acceleration of cosmic expansion is driven by dark energy, and we still don't truly understand what dark energy is. If voids represent regions where dark energy is stronger, where the vacuum exists in a higher energy state, then as the universe ages and voids grow larger, encompassing more and more space, the expansion rate might accelerate faster than current models predict. The European Space Agency's Euclid mission, launched in 2023, is mapping the three-dimensional structure of the universe with unprecedented precision. By 2027, it will have measured the positions and properties of billions of galaxies, allowing us to create the most detailed map of cosmic voids ever made. This data will test whether voids are growing faster than standard cosmology predicts. If they are, we'll know that something fundamental about our understanding of the universe needs to change. We stand at a threshold. The next decade of observations will either confirm our current model of the cosmos or force us to confront a more complex, more strange reality, one where empty space is the most important player in the cosmic drama. But the most profound implications emerge when we consider what these findings mean not just for the universe, but for the nature of existence itself.
Consider what we've discovered. Vast regions of the universe where space-time exists in a fundamentally different state. Regions that are expanding faster than the rest of reality. Regions that leave imprints backward through time on the cosmic microwave background, connecting the universe's present to its earliest moments in ways that challenge our understanding of causality. These aren't just empty spaces between galaxies, they're windows into the quantum nature of reality itself. Here's the most mind-bending implication. If the vacuum can exist in multiple states, different phases like ice and water, then there might be other phases we haven't yet observed. States of space-time with properties wildly different from anything we've encountered. Some theoretical physicists propose that our entire observable universe, everything we can see, all 93 billion light-years across, might be just one region in an inconceivably larger space, a bubble where the vacuum exists in one particular phase. Beyond our cosmic horizon, the vacuum might exist in different phases, creating regions with different laws of physics, different fundamental constants, perhaps even different numbers of dimensions. The cosmic voids we observe might be the first hints of these other regions, places where the vacuum is transitioning from one phase toward another. This connects to one of the most speculative but tantalizing ideas in modern cosmology, eternal inflation and the multiverse. In this picture, the Big Bang wasn't a single event, but an ongoing process happening throughout an infinite space. Different regions of this larger space inflated at different rates, creating countless bubble universes, each with potentially different physics. The voids we observe might be regions where our bubble is beginning to transition to a different state, the first stage of a vacuum phase transition that could eventually transform vast regions of space into something entirely different.
If this is true, then the voids aren't just curious structural features, they're evolutionary processes, cosmic metabolism, the universe literally changing its fundamental nature. There's a darker possibility. Quantum field theory allows for the existence of what physicists call false vacuums, vacuum states that appear stable but are actually metastable, capable of suddenly transitioning to a lower energy state. If our universe's vacuum is false, if it's not in its lowest possible energy state, then somewhere, sometime, a true vacuum bubble could spontaneously form. That bubble would expand at the speed of light, converting everything it touches to the new vacuum state. Inside that bubble, the laws of physics would be different. Atoms might not be able to form. The fundamental constants could shift to values that prevent any complex structures from existing. Some cosmologists wonder if the largest voids might be early-stage vacuum bubbles, regions where space-time is beginning to transition toward a different state. If this is true, then we might be witnessing the beginning of a cosmic phase transition that could eventually consume the entire universe. This scenario, called vacuum decay, represents one possible ultimate fate for our cosmos. But there's a hopeful interpretation, too. Perhaps the voids are proving grounds for new physics. Perhaps by studying these regions where space-time behaves differently, we'll discover principles that unite quantum mechanics and general relativity, the theory of quantum gravity that physicists have sought for decades. Perhaps the voids hold the key to understanding consciousness, or the nature of time, or the origin of physical laws themselves. The universe is teaching us that empty space isn't empty, that nothing isn't nothing, that the vacuum between stars is as rich and complex as the stars themselves. We've built our civilization on solid ground, under predictable skies, assuming the universe follows consistent rules everywhere. The voids challenge that assumption. They suggest reality is stranger, more varied, more alive with possibility than we imagined.
From Gregory Thompson's accidental discovery in 1978 to the cutting-edge observations being made today, we've journeyed through evidence that transforms our understanding of cosmic architecture. The voids aren't empty spaces, they're active structures where space-time exists in a different quantum state. They're expanding faster than the rest of the universe, pushing against the cosmic web, potentially determining the ultimate fate of reality itself. They comprise 80% of the universe's volume, meaning most of existence occupies this mysterious state, not the dense star-filled regions we call home. We are the exception, not the rule. The current scientific consensus holds that voids formed naturally through gravitational collapse, but are revealing physics we don't yet fully understand. The anomalous expansion rates, the cold spots in the cosmic microwave background, the strange gravitational effects, these observations are real and require explanation. Whether that explanation involves new physics, modified gravity, or a deeper understanding of the quantum vacuum remains to be determined. But one thing is certain, we can no longer treat these regions as mere empty spaces between the interesting parts of the cosmos. The voids are the interesting parts. They're where the universe is showing us its deepest secrets. In the darkness between galaxies, in spaces so vast that light travels for hundreds of millions of years without encountering matter, space-time itself transforms. The vacuum changes. Reality shifts its fundamental nature. And we are beginning to understand. The universe is vast. The mysteries are endless. The journey continues.